Welcome everyone to the third What is talk for this semester. And today's speaker is Professor Chandrasheel Bhagwat. He's an associate professor at IISER Pune, and he's also the faculty coordinator of the IISER Pune Math Club. So that's nice. His research interests lie in various different fields. So they span from number theory to representation theory, 12 functions, and spectral theory of differential operators and graph theory. Today he'll be talking to us in particular about the last, uh, something that relates to the last two things, which is spectral theory and how the subject is often useful in its own research. Before starting the talk, I'll just tell everyone that we are recording the talk, and it would be great if you could keep your cameras off and your mics muted. Um, Professor Chandrasheel has would prefer that the questions be asked in the chat window, and then we can ask. So then he can answer them in the end, or whenever he stops in between for questions. And if you would really like, then you can interrupt him and ask questions directly by turning on your microphones. Now it's almost 6:10, so I think we can start. Over to you, sir.
Okay, so thanks to Math Club student team for inviting me to give the talk here. So it's really a wonderful initiative taken by the Math Club to have the series called What is the Subject? I think there have been some very great talks in this series, and today I'm happy to give a talk on my favorite subject, so to say, called spectral theory. So if you open the English dictionary or talk to a layperson and ask what is spectral, then you'll often get a very terrifying answer. So the spectral is typically used in the context of what is spectre or ghost, or let's say something which is evil. In the same spirit, there are two particular things in math which go by the adjective spectral. One is spectral theorem, which today I will at least try to demysterize it and make it accessible in the as easy language as I can. The other often terrifying object is called spectral sequences, which today I won't talk about. It's not really part of spectral theory, but the adjective is exactly same, and both have terrified people, including students, faculty, and researchers alike. So with that brief comment about the word spectral, let me begin the talk. So just one quick remark. So the Math Club had organized a symposium called Abel Symposium, which was about Abel Prize winners. That was, I think, 1 year and few months back. That time nobody had heard of the now infamous word corona, and my talk was titled as this. Yeah, I forgot the exact spelling. Maybe it's O. So all these three words had different meaning in English and some related meaning in mathematics. And I talked about Carlsson's work. Carlsson is a Abel Prize winner, a mathematician from Sweden, and I spoke about his work, especially this work, which has terrified all of us since last 1 year. So hopefully, after today's talk, there won't be anything spectral which is going to happen. Anyway, so with this grim note, let me come back to mathematics. So, as I said in my introduction to the talk, the spectral idea, the spectral phenomena are abundant in nature and in our daily life and also in mathematics. So I'll not spend much time on describing them, but I'll just talk about a couple of things which are going to be related to what I'm going to speak for next 1 hour. One is, of course, it's a common theme where something which is periodic gets broken into, or it's a superposition of simpler functions, which you see in sound waves, electronic equipments, and in general electronics. And also in optics, where there's a phenomenon called dispersion of a light, where according to the wavelength, the light gets broken into various colors, and that is also known as spectrum. So all these things have a common theme, and I'm going to relate that with some more classical ideas in mathematics. So what is the idea? You have something, and now I'm fortunate to use my iPad here so that I can draw different colors. I'm drawing them in random order. So this is not exactly how your rainbow looks like. But you think of something which is made up of these three colors, and then let's say it gets broken into various colors, where each patch is a little more simpler than the whole thing. That's the main idea of spectral theory, and it's let's say it's visible when you look at these kind of mathematical objects. Sorry. Now, they're not really, yeah, I mean, they're kind of something which happens in real life, and then the mathematics behind that is related to how the spectrum looks like, etc. The other more pure mathematical point of view about spectrum goes into the modern foundations of algebraic geometry, where I'll not go into a lot of details. This talk is not really about this aspect, but since the word spectrum appears there, I feel like saying a couple of things, and they have a similar flavor. So let me take one example. So this is some number which just came to my mind. So this number, you can write this as 2 cube into, yeah, I hope I'm getting it correct. So I'll do a quick calculation in mind. Yeah, so this is how the prime factorization of this 1080 looks like. So the idea, just try to appreciate the idea. Here something was broken into three lights. Here something is broken into power of product of prime powers, where there are three distinct primes you see. Similar decompositions happen in algebra. For example, polynomials can be written as product of something called irreducible factors, which I won't right now. I'll come to polynomials in a short while in a different context. The other thing is, for example, you look at these two lines. So suppose the equations of these two lines for simplicity are y equal to 2x and y equal to, let's say, minus 3x. Okay, so this is like a graph of some particular curve, not really curve, but it's like a, let's say, union of two lines. And you can think of each line, this is like an infinite line. I've not drawn the full thing. So this is an infinite line, this is another infinite line. And in some abstract sense, one can talk about these lines being irreducible objects. You cannot break them algebraically into smaller objects. Whereas this whole thing is itself not irreducible, it's like union of two irreducible objects. So with this precise meaning, one can relate this spectral phenomenon in, let's say, this kind of algebraic geometry. This is, let's say, arithmetic analog of spectral theory, spectrum, and this is, you can say, algebrogeometric analog of decomposition, irreducibles. Now, I'm not going to talk much about this aspect, though it is very interesting. Let me go back to more classical kind of mathematics, where what I'm going to talk about, these kind of objects were studied. So now I'm going to introduce a few notations. So I'm basically going to assume that everybody in the audience is familiar with matrices, linear equations, and differential calculus, like derivatives and partial derivatives. If you have some particular question which is bothering you, you can stop me and ask, or you can type in the chat window. We'll take the questions in the end in more detail. So the example that I'm going to talk about, and this is really one of the biggest motivation in the study of spectral theory. So the question is, or the situation is like this. So let's say that linear algebra, comma, calculus, motivation. So the situation is very simple. You have some set X. Don't worry about what kind of structure is on the set. Later on, we'll make this more refined. Right now, just a set. And V is all functions from X to complex numbers. If you are not, let's say, if you don't like complex numbers, for this example, you can replace them by real numbers or any field. What I'm going to say is purely algebraic. There is no actual differential calculus needed for this example. So you can just call it whatever field you like. And then you fix some function g in V. Okay, so what does g do? G takes a point in x, maps it to a complex number. It does it for every point in x. So you fix that g. So I'm not going to temper with this g. And now I'm going to define something called multiplication operator. So what is that doing? So this mg, let's denote it by mg. Mg will take f to g times f. So it just multiplies a given function in V by g. It does it for every f. This mg turns out to be a linear map with appropriate scalars. So if you are using complex numbers like I defined, this will be complex linear. If you are using a different field like real numbers here, it will be real linear, and so on. Okay. Now let's ask ourselves a question. So first of all, just to bring the things into proper perspective, let me recall a familiar notion called range of a function. So range of function g is the set of all values in complex numbers which are taken by this g. So this will be of the type g of x, where x is in x. So I'm not thinking of little x and capital X as variables here. Okay, often we think of these as variables. In the later part of the talk, I might switch to these being variables. Right now, they're just thought of as this as a point and this as a set. So g of x is not really a polynomial kind of thing. It's just a complex number which is evaluated. So this is the familiar thing. Now the question which we are interested in looking at is, when is inverse of mg defined? Okay, and more, let's say, let me parameterize this question by not just looking at mg, but I will talk about a slightly different variation of this. So let me just change it here. So what you do is that you look at g minus lambda, where lambda is a complex number. And what is mg minus lambda doing? It's going to take f to g minus lambda times f. So that means at a point x, this guy is going to be just gx fx minus lambda into fx. That's it. So this is a symbol for all. I'm going to just use it and say for all. So for every complex number lambda, you define this, and then the question is, when is this guy when does this guy has an inverse? Go back to the definition. What does inverse mean? Given an f, you obtain gx by multiplying it by g on left. To invert the process, you have to, of course, multiply by g inverse. Similarly, if you want to invert mg minus lambda, you have to multiply it by, so the inverse operation has to be the inverse of g minus lambda in the multiplicative sense. That means you have to multiply by 1 over g minus lambda. So using this theme, you can do a small exercise and check that the answer is exactly this. So when can you invert gx minus lambda? Exactly when gx minus lambda is non-zero. Okay, if it is 0, you can't invert. If it's non-zero, you can invert as a number. And hence, the answer to this question is that exactly when lambda is not in the range of g. So range is the set of all values which are taken, and if lambda is not in the range, then you can invert gx minus lambda at every point and hence as a function. So this is a very simple-minded question and simple-minded answer, but this gets very closely related to the spectral theory. That's what we're going to see now. I will come to a more familiar situation, which is really a special case of what I did in some precise sense. So I hope that all of you have seen the idea of what is an eigenvector and eigenvalue of a matrix. So for matrices, so you look at, I'll not go into the order of the matrix and what is the field and so on. These things are not so relevant in this discussion. So the determinant of, let's look at the following thing. So look at the determinant of t minus, now I'm going to use little x as the variable. If it's going to confuse you, let me use little y. So you think of y as a variable and you look at the polynomial determinant of t minus y times identity of the same order of t. So t is a square matrix, so that we can talk about determinant. So you look at this equation and the solutions of this equation are called eigenvalues of t. And one can define the notion of spectrum of t this set. So you think of, you look at the set of solutions of a polynomial equation. The general theory tells you that such solutions always exist, at least one solution is there. And in fact, the number of solutions, if you count correctly, will be exactly the order of this matrix T. So there's one question about fundamental sum of algebra which just popped up. So I'll come to the question later, but the fundamental sum of algebra is exactly this, which says that when you are working with C, you get solutions of these equations in C. And how many? Exactly the same as the order of this matrix T, if you count with correct multiplicity. And the spectrum of the matrix is called this set. And in fact, the origin of the word spectrum has to do something with the eigenvalues of various operators which come in quantum mechanics, but let's not go into that today. So the spectrum of T is exactly this set. And this is also, you can now think of inverting elements. Now the determinant being being 0 is same as saying that you cannot invert. So let me write it. This is same as set of all lambda such that T minus lambda I is not invertible. Okay. So this is how the previous question and this question are related. The previous question, we said that if lambda is not in the range of G, then you can invert mg minus lambda. And if that also means that when you can't invert mg minus lambda, that lambda has to be in range of G. And similar statement is there for matrices. And hence, we can, in general, define spectrum of a linear map. For example, the spectrum of mg, which I talked about earlier, is defined. So this word is not meaningful unless we give the definition. So the spectrum is defined to be set of all lambda such that mg. So I'll write something here which is obvious, but you just think about it. So if I subtract lambda times identity from mg, that is same as mg minus lambda. So this is not invertible. So not invertible in this context also means that it's not bijective. It's a map from V to V. It's going to be linear. If the inverse exists, it's going to be linear also. But what we want is the inverse should exist as a function. And that is same as that it's a bijection. So this is the key idea. So you talk about linear maps in this context, that you want a number to be in the spectrum of the linear map if the map minus that real number time or complex numbers time identity is not invertible. All right. Now let me come to the main idea of spectral theory, which is in some sense going to resemble with the light dispersion and sound wave being superposition of various smaller waves and so on. All that will be seen in this statement. So let me talk about one aim of spectral theory. So this is what I'm going to say here is a statement about linear algebra and linear maps, but similar themes exist in other contexts, which will come to in the later half of this talk. So the spectral theory aims at the following thing. So let me be a little brief here. I don't want to convert this into a full flow lecture on spectral theory. I'll just say the bare minimum essentials. So what you want is, for example, you think of a matrix T, and you can think of this matrix T as a linear map from Cn to Cn. C linear map, because we are talking about complex numbers, but you can replace C by any field, as I said earlier. What I want is I want to describe Cn in the following way. So I'm going to use some symbols, but it exactly is what you think about. So I'm going to write this as with this symbol called direct sum. So what I want is I want to break Cn into smaller subspaces, vector spaces, such that the ith, let me reserve I for complex number if needed. The jth space is exactly, I'll not write this as an equation, but I'll say what it is, such that if you restrict your T to V lambda j, it just gives you lambda j times identity. So what's happening is that I want the Cn is the given big vector space. I want to write this as direct sum, whatever that is. If you know it, it's fine. Otherwise, you just think of this as decomposition of a big space into smaller spaces. So that each of these should be a vector subspace. And if you restrict T to this guy, it should be as simple as possible. Namely, it should be just scalar multiple of the identity. And lambda j's are, of course, numbers because of this property. So lambda j's are complex numbers. And we want them to be distinct, because if they are same, then you can always club together. Now, unfortunately, this is not always possible. Otherwise, there is no relevance to the spectral theory and spectral theorem. Because, yeah, if it is true for every map, it's just a property of linear maps, but that's not true. You can think about various examples. Let's not go into the specific examples today because of lack of time, but you can, if you don't know this fact, you can believe me that there are maps for which such a thing is not always possible. So now the question is for which maps it is possible, and I'll just say something which is, so I should say state at least one theorem very precisely, which I'm going to do now. After that, everything will be more heuristic. So the theorem, it's also called spectral theorem. This is not the spectral or terrifying version of spectral theorem, because it is for complex numbers and finite dimensional spaces. It doesn't look scary at all. So the spectral theorem says that if T star equal to T, I'll just say in very short notation. So what is T star equal to T means? It also has a name. It means this condition is same as saying that self-adjoint linear map. So what I do is that I'll just tell you, for those who don't know what is the adjoint of a matrix, I'll just tell you what it is. For linear maps, there's a similar theory. So what you do is that you take a matrix, you change the rows to columns, that's called taking transpose, and then take complex conjugate everywhere. Such a thing is called the adjoint of a matrix. And then if a matrix is its own adjoint, it's called self-adjoint. And self-adjoint maps are nice, namely in the context that of the spectral theorem, that you can always write the self-adjoint map or self-adjoint matrix. For that, you can always write Cn in this form. Okay. In general, if this is about linear algebra, you should replace Cn by n-dimensional inner product spaces over C. But let me not go into very technical language describing everything in this talk. Maybe in the question answer session, we can take up these things again. So the self-adjoint maps are good. For them, the spectral theorem holds, and we are in good shape. I will mention something which is important, and all of you should know it. So there is a spectral theorem for infinite dimensional spaces. Let me just say those words. I'll just say that for self-adjoint maps on Hilbert spaces, so I'll write one scary version and one let's say, demystified version where it just looks very simpler. So you can write this t as integral of some function called lambda on spectrum of t with something called spectral measure, which doesn't make any sense at this moment. I don't want to think about this. So the brief one-line description is that here you are writing Cn as a direct sum or decomposition of vector spaces. On each part, T is going to look like a scalar map. So you can think of T as a direct sum of these lambda j's in some suitable sense. And the sum is getting replaced by an integral. And what this is and all these things are the, yeah, I mean, I don't think that's spectral, but it has some myths that spectral theorem is really scary. Anyway, don't worry about this. So what we want to say is that, so I'll just write one, or rather draw a diagram, and that's really the spirit of the spectral theorem. So this means, in the easier terms, I'll just write something and say that that exists, and that is the spectral theorem. So you have this H, maybe I'll call it Hilbert space, let's call it H. So you have a linear map from H to H, which we have called T. Then there is some space, let me just call it X for the time being. And then there is a vector space associated to that space X, let's call it Vx. And then there is some diagram like this. So mathematicians often like to describe the theorem using something called commutative diagram. So I'm just giving you a flavor of a commutative diagram. So this is the given operator. The theorem is saying that you can convert this problem into a problem about functions on a set and the same space appearing here. And then the MG map, which I talked about 5 minutes back, which is like multiplying some f here by g on the left side. So the spectral theorem is basically in one line. It's saying that either this, but if you don't like this, then it's saying that for h from t from h to h, which is self-adjoint, there is some space x and there is some function g such that this map t is exactly isomorphic to, in some organ, it's exactly same as mg. Yeah, so try to appreciate the simplicity of this statement. The proof is by no means simple, but the statement is very attractive and simple, that every self-adjoint map can be realized as the multiplication operator on some function space. And in my mind, this is really going to give you the idea of how the spectral theorem looks like rather than this guy. So those who are in the 4th year BSMS now, next semester you are going to get a course called Functional Analysis, which I'm going to teach, and you will hear more about the spectral theorem there. Right now, let's not worry about infinite dimensional Hilbert spaces so much. We'll go to more interesting objects. Yeah, so just keep and try to appreciate the basic theme of spectral theory, that you start with a self-adjoint operator, and then it will just look like multiplication by a function. So it simplifies in that way, and then we know how to handle these guys, hopefully, and try to understand decompositions of these type. We'll talk about some different kind of objects later, but right now let's leave the spectral theorem here. So let me take a 1 minute pause here, since I'm going to change the gears a little bit. All right, so let me proceed. Now the next, let's say, discussion about spectral theory is related to something called differential equations, namely, more precisely, something called partial differential equations. So those who really haven't seen much of calculus, so in calculus, one differentiates with respect to one function, and in the several variable calculus, you want to differentiate with respect to one function at a time, but there are more on one variable at a time, but there are more variables playing with each other. So such a thing is called, let's say, partial differential calculus. And many important questions in real life are formulated in terms of these PDEs. We are going to talk about one of the most important PDEs mankind has looked at, called the heat equation. The version which I'm going to talk about is the Laplace equation. It's really this equation where this guy, in its most simplistic form is the partial derivative with respect to, let's say, for 2 variables, it's like this, and for n variables, you can guess how it looks like. And in 1 variable, it is just the second derivative. So for some reasons, which you will hopefully appreciate at the end of talk, I'm going to put a minus sign here. So I want to make my Laplacian to be positive definite. So I lose the one minus sign to make that happen. So I'm going to just call it minus of this guy. Okay, so how does the spectral theory come into picture here? Let's try to solve this equation in the one variable situation. So suppose I want to solve the following differential equation. It's not really, it's very different kind of differential equation. We don't want one solution. We want to find, for example, what is lambda and then find the solution. So the second derivative of f should be lambda f. This is the equation. So the question is find lambda and then find f. In general, it's a hard question, but we want to simplify it by assuming that f is periodic. So this is some sort of condition that you put on f so that the solution will look nice. So it's related to, for example, the wave phenomena that I talked about in the beginning. So the electronic equipments, sound, optics, everywhere there is certain periodic motion which is happening, and simple harmonic oscillators is another example. And we want a periodic function f with period 2 pi. You will see why 2 pi and why not something better. But right now let's put this condition. I want to, as I already stated one theorem in reasonable precision. Now I want to show you one particular technique which is used in this kind of mathematics very often, because it's kind of a talk where you should see some of the serious mathematics getting used. So I'm going to be heuristic, but tell you how a particular technique is used in such things. So the technique is called using harmonic and Fourier analysis. So what we are going to do is that we are going to cheat a little bit. That means I will not justify all the claims I'm making. You can go back and check that these claims are indeed true. So I'm going to write down f as a Fourier series. Every step needs justification. So I'm already putting a disclaimer that don't worry about the precise derivation and arguments here. So you think of these exponential functions, which are really cos nt plus I sin nt, where n is varying over integers. Cos is even function, sin is odd function, so I have to involve all the positive and negative integers in the Fourier analysis. So there's a theorem which says that f can be reasonably expressed as summation n into e power I n t. Now I'm going to differentiate twice on both sides. So if at all f satisfies this equation, then the second derivative is precisely lambda f. So if I apply d square by d, I use t for some reason, let me stick to that. D square by dt square, I'm going to get lambda times f of t, which is nothing but I multiply everything by lambda. Okay, so I'm going to scroll to the next page. So just remember this expression. It's basically to multiply everything by lambda. On the other hand, if I cheat a little bit and differentiate this with respect to t twice, which I'm not going to justify here, why is it true? It is related to one of the things I talked about in the beginning about some previous work of Leonard Carlson. So you differentiate the right hand side twice. So you are going to get, you differentiate this guy twice with respect to t, you are going to get I square into n square, which is minus n square. I think I have to put a minus sign everywhere in the beginning so that I don't, so there should be a minus sign here because I'm looking at the minus, sorry, I'm goofing up a little bit here. Let me just clear it. So the delta for me is minus of the second derivative. So this is fine so far. So if I do the second derivative thing correctly, this is also going to be same as with a minus sign because of that I factor there, and then it's just a n into I power e to the power I n t. Now I'm going to cheat once more and tell you that we can compare Fourier coefficients without justification. So on one side, the Fourier coefficients look like lambda an, and then there is a minus sign here. So what you're going to get is that minus lambda an. Yeah, so now I have to be really careful about the sign. So let me see if I goofed up anywhere. Yeah, so there should be, so we are looking at minus d square by dx square f equal to lambda f. So far it's fine. And that side I'm going to get yeah, so I'm okay, that's fine. So whatever you can adjust the sign later if I booked up somewhere. That's fine. So if you compare the Fourier coefficients, I'm going to get the equality like this. And if you play around a little bit with this equality, you're going to get the possible values of lambda. Yeah, so somehow I must have grouped up the minus sign somewhere. So let me put a red mark here. You can change the sign correctly later as a homework and then make it correct. So the possible values of lambda, if you do this whole mathematics correctly, are going to look like 0. Then I'll write deliberately in a different way, 1, 1, 4, 4, and so on. So what are these? These are like squares of positive natural numbers appearing with multiplicity 2, and 0 is going to appear with multiplicity 1, and so on. So this is going to be the, so since I talked about d square by dx square as an operator, so what we are going to do is that this is going to be called the spectrum of Laplacian. So I'll write what sort of functions we wanted. We wanted periodic functions on real line. This is saying that functions on the circle. Okay. So here I'm not going into the geometry and topology, like how you can think of functions, periodic functions as functions on circle. The students who have seen some real analysis and topology, you should be able to see why this is happening. So this is how the spectral theory comes into picture. It's related to the spectral theory which I talked about earlier, but in more simplified manner. Here we are directly looking at the eigenvalue problem, and the solution to the eigenvalue problem will be that the eigenvalues will look like this, where you will get two linearly independent eigenfunctions with eigenvalue 1, two linearly independent eigenfunctions with eigenvalue 2, and so on. And this eigenfunctions, I'll not write everything here, but I'll just tell you that the eigenfunctions are just going to be sine and cos waves. So this is basically saying that we can, so the usual Fourier theory, that we can decompose a given signal or a periodic function into sine and cos functions, is exactly the restatement of the spectral theory here, that the Laplace operator can be written as its eigenvalues are going to look like this, and its eigenvalues are going to be cos and sine functions. So yeah, I mean, this is the basically what I've done here is that I related the classical Fourier analysis with the Laplace spectrum on the functions on circle. I'll very briefly tell you what happens to the other objects. So now I'll bring into picture the geometry. So I'll talk about two examples of interesting functions which I'm not going to talk about immediately.
So the geometry part of what I'm going to say is about the two geometric spaces called S2, which is the sphere, which you can think of as something sitting inside R3. Let me just say unit sphere in R3. So it's not the ball, it's really the boundary of the ball. So the inside part is removed, it's a hollow sphere. And the other thing is the famous shape called torus, which is, you can think of this as a tire tube or medu vada or donut, whatever you want to like. But I cannot draw it very nicely, so you have to just imagine that this is correct torus. So for these objects also one can study the Laplace operator. So I'll not go into definition of Laplace operator in these cases, because that I have to talk about something called Riemannian geometry in more detail for that. But just keep in mind that there is a nice Laplace operator which is normalized so that it is positive definite. And so in the case of torus, it's the usual Laplacian. It will be just del square by del x square plus del square by del y square. In the case of sphere, it's also like that, but little more complicated. And what happens is that there also the spectrum can be written down. So now I'm little behind the time. I have to talk about some other thing also. So I'll not right now talk about how the spectrum looks like, but I'll just tell you the theme. So the spectrum of, let's say, this lambda on S2 is determined. So I'll just say the punchline and then talk more about this in the question answer session. Is determined by the irreducible representations of group SO3. So you don't have to worry about what is representation theory and what are irreducible representations to understand this. What's happening is that I'll just tell you the theme, that's more important. What's happening is that you think of this as a geometric object. So it has got nice geometry in the sense that at, let's say, you can talk about distances, you can talk about distance minimizing path, you can talk about tangents, you can talk about angles between two lines and so on. Or lines will be replaced by something called geodesics, but the inappropriate language, you can talk about various geometric features. And then the SO3, what you should know is that SO3 is the set of, let's say, all rotations around some axis in R3. And such a rotation is going to give a symmetry of this S2. So however you rotate the sphere, as long as you are rotating around one particular axis, the points on sphere are going to stay on the sphere. They're not going to go anywhere else. They will move with respect to each other, but they'll still stay on sphere. And such maps are called isometries of the sphere because they preserve the geometry. And this forms something called a group. So those who know groups, you can appreciate the fact that the isometries of any geometric object will form a group. And the irreducible representations in one line are classification of various ways in which such a group will operate or act or give transformations of some vector spaces. And the irreducible representations of SO3 play a role in determining the spectrum. Same thing also happened in the previous example. Here the isometric group will be also the group of rotations in R2. It's called SO2. It is same as the circle group, and its representations are basically going to determine these numbers. Exactly same thing happens over here. The SO3 is a group, and its representations are going. They in fact determine the Laplace spectrum here. Same thing happens with the torus. In the torus case, the group is something called SO2 cross SO2. It's also called the torus group, and its representations are going to determine the spectrum here. So this is the key point which I just wanted to say here. Now we are almost in the last 1/3 of the lecture. So now I'm going to talk a little bit about some interesting ideas and theorems which go into this, and then I'll very briefly talk about some contribution which I have given as my PhD and the subsequent work. So yeah, I mean, there are some questions which are coming. I'll take them in the end. It's okay. So what we are going to do is that we are going to ask a question. Does the spectrum determine geometry completely? I'll just say geometry. Yeah, so this question can be asked in a lot of refined and different ways. I'll just put a loose question here and then talk about refinements. So what is the theme here? Here I said that once you know something about the isometries, let's say, or symmetries, from that you can say something about the spectrum. Now you can ask the converse or inverse questions where So for example, if you have a geometric object and you know its spectrum, from that, what can you say about the geometric aspects of the geometric object? I'll ask more precise question here, which is colloquial. The colloquial way to say this question is that, can you hear the shape of a drum? So what is this question really asking is that you had two objects. So let me not again go into the precise definition of what kind of objects one is looking at. The technical word is Riemannian manifolds, which are compact. So suppose you had two geometric objects. Both of them have spectrum, and the spectra are identical. Okay, so the spectrum is always the Laplacian spectrum, which I haven't defined, but it's some nice differential operator that one has. So you have this sequence of eigenvalues of the solutions to the Laplace problem, and here also you get the same sequence. The question is, yeah, I'll put a fancy thing. So we can ask question in many ways. So the first question which I asked here is that, can you hear shape of a drum? Which means that these numbers are in some sense represent the sound made by a drum. And you have two drums to start with. They make same sounds. The question is, can you hear the shape of a drum, in the sense that, can you say that the geometry of these two drums is its same? So this question became one of the very famous paper in 1960s, I think. Later on, there were a lot of study, there are a lot of interesting answers to this question come. In some cases, the answer is yes, but generic answer is no. And the systematic study of such a thing was made by two mathematicians, Sunada and Vineras. And also another famous mathematician, Milner, gave a class of drums or geometric objects which sound same, but meaning they have same spectra, but intrinsically they are different objects. And various techniques emerged later. Many of them use a representation theory of groups, and that's how I got interested in studying this subject of spectral theory of differential operators. So this is one glimpse of what kind of problems people study. The another glimpse which I'm going to give you now here, instead of going into all interesting questions here, is some of my work. So I'll just state another theorem, and then say a few things about some open questions in this direction. So this is a theorem which came as a part of my thesis, jointly worked with my advisor. And the theorem says this. So now I ask a different question. So suppose M1, M2, I'll just state this as a theorem, not as a question. Suppose M1 and M2 have different spectra. Then infinitely many eigenvalues, let me say spectral values because that's how they appear, have different multiplicities. Let me explain what does this mean. So suppose you have lambda 1, lambda 2 and so on, and mu1, mu2 and so on. I deliberately avoided the usual way of stating theorems where one starts with a lot of hypotheses and writes the conclusion as a one line. That won't serve the purpose in such a talk. So I just wanted to tell you in the, let's say, mellowed down language what exactly this is saying. So you had two objects, and then there are two sequences of the spectra, so spectral values. So suppose this is same as this, this is same as this, and so on, then we say that they have same spectra. Now let me change the question. Suppose the spectra are not same, but let me just give an example. So suppose the 1000th value onwards, they are same, but before that somewhere they may not be same. Okay, so look at this situation. That first 999 equations, some of them might be false, but after the 1000 and above, all the eigenvalues are same. So the theorem, which is my joint theorem with my advisor Rajan, says that this is not possible. If they are different, they have to be different at infinitely many places. It cannot happen that only many are possibly different, and after that they are same. So unless you know something about similar theorems in automorphic forms and number theory, it's hard to appreciate such a why such a theorem should be true. That I also understand. That suppose suddenly somebody shows you such a theorem, then you will ask why. So what? So that's a very valid comment. But once you see similar themes in other parts of mathematics, you will appreciate more. So this is one theorem, and there are many theorems, and I'll write some context in which some of my work has proved such a theorem. So similar results. One is about, I'll not talk about the representation theoretic part here because that's slightly different in flavor. So something called length spectra. So here what I do is that I looked at something called hyperbolic spaces, and then you, instead of talking about Laplace eigenvalues, you can talk about lengths of geodesics on these spaces. So this is now becoming more technical. I have to define so many words. What are hyperbolic spaces? What are geodesics? Geodesics are just length minimizing curves. Hyperbolic spaces are something which have negative curvature. I'll just stay put with this much. So there also similar theorems are true. Then, so I also studied similar things for, let me be short here. Also for something called graphs, which are very different objects. They're like discrete objects which represent networks mathematically. There also surprisingly such theorems hold. This was my joint work with my PhD student. And third thing I would like to mention is the spectrum of Laplacian. So I'll just use the word delta for the general Laplace operator without defining it. So my previous fifth year student Nazia, who I believe is in the audience, so we studied the idea of what is spectrum of such Laplacian for certain graphs and whether similar results are true. So there's some ongoing work, and we are hopeful to prove similar theorems in that direction also. I'll just like to end with some open questions which are of interest of many people. So we can discuss a little bit more in the question answer session on this aspect. So how is representation theory? So I'll not write everything here, but what I mean is, so there is something called a representation theory of a group, and there is something called spectral theory of differential operators. In how much generality do they determine each other? So if you know everything about spectra, do we know everything about representations? If you know everything about representation theory of that group, then do we know everything about the associated Laplace spectrum? These kind of questions. The second interesting kind of question is how small lambda 2 is. Okay, so I'll just put this question in this very vague format. So the motivation is something like this. So the lambda 1, which is the smallest eigenvalue, so I'll write like this. So what is known is that the first eigenvalue is always 0, for the stupid reasons that you just look at the function which is constant 1 everywhere. Such a function, if you differentiate whatever number of times, you are going to get 0, and 0 will be the eigenvalue of such a function, and hence the first eigenvalue is always 0. And since it's a positive definite operator or matrix, whatever you want to think about, the further eigenvalues are going to be strictly positive. And the question is how large or how small this guy is. There are many variants again, but one interesting part is how small this lambda 2 is for a, let's say, given set of, I'll just use the word Riemannian compact manifolds. I'm more interested in the hyperbolic situation, so I'll say hyperbolic manifold. And this is closely related to some other conjectures in automorphic forms and number theory, closely related to something called Ramanujan's conjecture, which has been now proved in the context of modular forms, and so on. So yeah, I mean, these are the some of the things which I wanted to talk about. So let me stop from my side here. Let me take a 1 minute break. I'll have some water, and then we can discuss questions which are in the chat. Okay, so why don't we just go through the questions which have been asked in the chat window one by one? That's a better way to go about it. So there has been some discussion also. So let me not go into the discussion at this moment, but I'll just have a question. I'll have a look. Manraj asked something about your version of T here is Ritz representation. So Ritz representation theorem is used in the, let's say, proof of this theorem. So maybe, that's one line answer to your question. It's not exactly Ritz representation theorem. It's something on the similar scale and similar theme. Manraj, yeah, you have something to say. Go ahead. Yeah.
So that point where you described the general spectrum theorem sometime before, you wrote the operator T as that integral. Yeah, that integral. So what is, so if you take an element X in the domain, then what is Tx here?
Exactly. So it's not a function of real. It's not a real valued function. So what we are doing is that, so something called integrating the real valued function with respect to a measure. Here we are not integrating real valued functions. Here we are integrating operators. So for example, for every subset of this T, you associate a linear map, and then there's a way to talk about integrating linear map valued functions, and that makes it more complex to understand in some sense.
So you're integrating on a functional space in a sense.
Yes. So the idea is that the usual measure is related to functions, and then we can, so for example, such a dp lambda will be determined by a certain family of usual measures, one for each vector in the vector space.
Oh, okay.
Yeah. So think of this, so just to come to, so for example, in the classical version, there are this v lambda 1, v lambda 2, and so on, right? So if you look at the projection on v lambda 1, projection on v lambda 2, and so on, they give you m different linear operators. And if you integrate, so that defines something called operator valued measure. And then you integrate the function lambda 1 to lambda with respect to that measure, and then you're going to get your T back.
Okay, so how does this relate to the, so I have seen one version in my functional analysis course. There is this on self-adjoint compact operators.
Yes.
How does this relate to, this is a more general version.
Yeah, exactly. That's a good question. So for the compact operators, it's exactly the countable infinite analog of what happens here. That you have one eigenspace, which will be the zero eigenspace, which could be very huge. Everything else is a finite dimensional subspace. And then what happens is that you are projecting, so so each of them has a projection, and then this version is basically saying that the spectrum sigma t is a countable infinite set, and then for every point in sigma t, you have a projection associated.
Okay.
So it's like a countable set on which operator valued measures are going to be defined. Yeah, so this is, I think, getting a little technical. So maybe I'll speak to Manraj later and with more details. Yeah, we can correspond over email later. There has been some discussion about irreducible spaces, which I promised Sridhar that I'll come in the end. So I already mentioned the positive definite operator part. So what you do is that you look at, so what is Laplacian? So again, I didn't say much about that. So you can think of Laplacian as the unique operator up to scalar, which is going to commute with all the symmetries. So for example, in the R usual real line, there are translations and there are reflections. And then you look at all the operators which commute with, all differential operators which commute with such symmetries. And then there is a unique second order elliptic operator going to do the job. but you can adjust it up to the scalar. So the tradition is to make it positive definite by multiplying it by minus sign when needed. So if you do the math, which I might have goofed up a little bit in this derivation, so if you do the d2 by dx square math correctly, then you will see that the eigenvalues are negative, and hence you multiply it by minus sign. Okay, so Vishak is asking a question about irreducible representation.
What is sigma of t here?
Sigma of t is the spectrum. So I think I said that sometime back. So you look at any linear map, and then you look at all lambda such that t minus lambda is not invertible. So yeah, so for any linear map, you can define the spectrum by that. It's called denoted by sigma of t. Sigma is like the Greek letter for it. So, yeah, maybe didn't define that, but that's all. So Vishak is saying that, asking that, how is the spectrum of spherical Laplacian related to the irreducible representations of SO3? So again, it will go into a very technical discussion, and it's a good question, but it demands more detailed answer if I want to give justice. So again, in short, what's happening is that SO3, you can think of this as a group of symmetries of S2, and then your Laplacian is in some sense going to commute with the action of SO3. And what you do is that you look at the functions on sphere and then see how SO3 acts on it. Then again, it will decompose into finite dimensional subspaces, which are called irreducible subspaces. And then you ask which irreducible representations of SO3 are realized in this decomposition. And then SO3 representations are parameterized by odd numbers like 1, 3, 5, 7, and so on. So for each odd number, you are going to get a, so let's say 5, then you are going to get a 5-dimensional space inside the function space on SO3, so on the S2, and then that's going to give you the eigenvectors for the Laplacian. The technical keyword one wants to look for is something called spherical harmonics, or the harmonic polynomials on sphere, and they are going to give you the eigenfunctions. So the representation theory comes into picture because you want to decompose the function space on sphere as the representation of SO3. So the previous question is again a big question. So there is something called geometric spaces. So I'm not going to go into that at all. So there are so many aspects of the geometric spaces that so for example, very what is relevant to this talk is that something called a manifold, where you can do the calculus and you can do something called Riemannian manifold, where you can do the geometry locally. So you can talk about tangent spaces, angles, and so on, and distances. The algebraic geometric spaces are very different. I'm not going into that today. So Manraj is asking how small lambda 2 is. Yeah, I mean, this question is interesting to people who work in analysis, PDEs, also graph theory, because they're related to graph theory. Then the number theorists are interested because certain manifolds can be obtained using arithmetic subgroups of various Lie groups and so on. So I don't know exactly what context Manraj is talking about. So this is in some sense, I think, about PDEs of involving elliptic operators and so on. So yeah, Manraj, if you have to, if you want to say something more, you can say. I at least don't know much about this aspect. Yeah, Srijit, you have a question?
I have a question. Somewhat, it's coming from a physicist, so it's maybe inherent vagueness in it. So, at least in physics, there are operators that have continuous spectrum and sometimes a discrete spectrum, and sometimes there are operators with a mixture of the two. So is there any general theorem or some rule that tells me when I can get a discrete spectrum and when I get a continuous spectrum? And a couple of other related questions. So if there is a discrete spectrum, how do I think about degeneracy? So if there is a continuous spectrum, how do I think about degeneracy? If there is a discrete spectrum, I know that a particular eigenvalue repeats itself, and then I know there is a degeneracy of n, and then so how do I think about it there? The third question, let me just complete that because it's probably related. So you when you looked at the eigenvalues of the Laplacian, you sort of put in the boundary condition for the f of t function. So why, if I insist that I don't want to put a boundary condition, I want all kinds of boundary condition, then is there no spectral theorem? Is that?
No, meaning I'll kind of answer the questions one by one. So the first question was about when is the spectrum discrete and when it is continuous.
Right.
It's related to something called compactness of the original setup. So for example, there are two things I can think about. One is something called compact manifold. So you think of sphere, torus, everything as something called compact topological space, whereas R2, R3 or open disk, these are like non-compact sets. And on compact sets, the spectrum is, the compactness ensures that the spectrum of Laplacian is in fact a discrete set. Similarly, there's a notion of compact operators on Hilbert spaces. In that context, also one knows that the spectrum is a discrete set, except 0 will be an accumulation point. So the eigenvalues will come near 0, but apart from that, they will be like isolated. And in the degeneracy part of the continuous spectrum, so for example, the spectrum could have all the real numbers between 0 and 1. So in that situation, one really cannot talk about those numbers as eigenvalues. So I'll try to be a little vague here, so it's difficult to describe these things very precisely. So what's happening is that this multiplicity which one talks about of an eigenvalue, you can think about the weight given to one point. So for example, if 5 appears with multiplicity 7, that means you're giving the weight of 7 to that one point. In the continuous situation, the closed interval 0, 1 will get a weight, but every point doesn't get a weight. So it's like the probability theory of continuous random variable, where one particular number doesn't get any probability or weight, but the subsets like closed intervals or open intervals, they get weight. And then you can talk about the degeneracy or multiplicity in that context. So there is no multiplicity involved, but there is something called spectral measure, which I alluded to in the statement of spectral theorem. So there is a certain function, or not even function, there is something called an operator valued measure, which is associated to that interval. So that's how one, in my opinion, that's how one addresses the question of multiplicity and degeneracy. Now I forgot the third question.
Third question was you put periodic boundary conditions and then ask for the eigenvalues.
Right. So essentially, the periodic boundary conditions was a cheap way to say that the function is defined on a circle. So you can think about so if something is periodic, you can just make it into a loop and think of
but let's say the functions are on the let's say I don't want to impose periodic boundary condition. I can use twisted boundary condition, right?
So for example, with the boundary conditions, the solution to this differential equation, lambda partial differential equation, lambda f delta f equal to lambda f, is guaranteed to have some solutions. But without any boundary conditions, if you allow, for example, if you allow functions to behave differently on the boundary, suppose you look at the situation where there is a boundary of some domain, and you want, the first question is Dirichlet boundary condition, which means that the function should vanish on the boundary and it should satisfy a PD. Then there is a general theory to do that. But if you allow the functions to have no boundary conditions, they could behave arbitrarily on the boundary, then of course the original solutions will still be solutions, but then it will become much more bizarre. And I don't know much about the general theory in that situation, but I believe that there is no general way to describe the eigenvalues.
Okay. Thank you. So we keep using spectral decomposition and spectral theorem very carelessly in physics, so it's quite nice that you.
But and on the same note, what happens is that in physics, so for example, the differential operators are more relevant in some sense. In usual, let's say, functional analysis, which are undergraduate studies, one often doesn't go to study of these kind of operators. One studies more easy operators like compact operators and so on. So in some sense, physicists use more sophisticated mathematics, but they don't have to go through the whole general theory of simpler operators. That's often observed.
Okay, thank you.
Yeah.
So
Go ahead. Yeah.
yeah, so in the beginning, you took the example of prime factorization of integers, right?
Correct.
And later on, when you defined the spectrum and everything, we did that for a linear operator. So how do you define a spectrum for?
Yeah, so that was not really, this is like, so that was not really about the linear algebraic part of the spectrum. So the relation is something like this. So you think of, so this is again a very, possibly going into a very long discussion, so I'll try to be brief. So what you think is that, so I'll take help of the picture which is drawn at that bottom. So here, what I'm going to do is that I've written some equations, y equal to 2x and y equal to minus 3x, which are like polynomial equations. And then I'm going to look at something which is defined by either this or both. So it's like defined by a pair of two equations of two lines, and then that's why I'm getting a pair of lines. So this is something similar to taking 2 into 3, because so here what I'm doing, here I'm, for example, I can talk about all the, let's say, all polynomials which vanish on this set. So you look at all the points here, this point, this point, this point, this point, and you look at all the polynomials in two variables which take value 0 at those points. So that is a space of certain polynomial functions. That is something called a ring, which has nice algebraic properties similar to the integers. So I think that's a good way to see the connection between this aspect and this aspect. So the idea is that, I don't want to go into technical definitions here, but the idea is that the irreducible polynomials are like prime numbers, and then you can build out geometric spaces just using the prime numbers and 0, or all irreducible polynomials and something called irreducible algebraic sets and 0. So I just wanted to talk something about this, because that's another place in mathematics where one uses the word spectrum.
Right.
And there are some similarities. For example, in the eigenvalue problem which I talked about for matrices, the way eigenvalues are found is by factorizing a polynomial into irreducible components, and then the factorization is exactly, let's say, linear algebra analog of prime factorization. So that's how they're related.
Right, and all the other places where spectral theorem is used, so everywhere there is some sort of a connection, and then you can basically take that problem into its linear algebra analog and solve it there.
Yeah, most of the spectral theory questions are about this idea of spectrum of a linear map.
Okay.
So the word spectral theory often is used in that context. The spectrum is used in some other context, which one of them I described here. There's something called spectral sequences. So that's little more category theoretic. I'll not go into that right now. Okay. The spectral theory, by that one means often some space, often a function space, often an operator which is like a differential operator or a matrix, and studying its eigenvalues and eigenfunctions or invertibility. Those things are studied in the spectral theory.
Correct. Thank you. And
yeah, other questions? We can discuss for a few more minutes if somebody has any question.
So, hello.
Yeah, Manraj, yeah.
So could you describe again how, like you'll call the Laplace operator as positive definite? I mean, how would you go about proving this?
No, it's a definition. So so for example, the proof will, the fact is something like this. You have some domain and has some symmetries of that domain. Now, the theorem that one proves is that the space of all operators of certain nice kind, namely second order, elliptic, whatever that is, which commute with these symmetries, that space is one dimensional. That's the key result that one goes into proving it. And then as soon as you have a one-dimensional space, whatever you define, whatever element from that one-dimensional space you pick up, you can change it by multiplying it by scalar. So I can define, if I like pi, I will say that pi d2 by dx square is my Laplacian. You will say that minus 300 into d2 by dx square is your Laplacian. So that's why there is some normalization needed. And one way to so the normalization doesn't affect the eigenvalues and eigenvectors. It will just, it doesn't affect the eigenvectors. It will just change the eigenvalues by appropriate scalar. And in the context I talked about, it really matters whether you take positive or negative. And then, yeah, so you make it positive definite by, if it is already not positive definite, you multiply it by -1. So one quick thing, since you asked the question, let me go to the last page. So something like this is true. So you look at d2f by dt square times g. So those who don't know about inner products, you won't appreciate this comment. So you look at this integral. So if your functions are nice, namely, let's say they vanish at infinity in some suitable sense, then you apply your usual by parts integral, and then you are going to get minus of df by dt into dg by dt. Whereas if I put a minus sign here, this minus sign vanishes, and if I look at just f instead of g, then I'm going to get such an equation. So this is the meaning of positive definiteness here. So the usual d2 by dt square is positive definite because of this reason. When you are applying it on certain nice functions which vanish at boundary. But the given geometric setup where there's a manifold, there's a Riemannian metric, and there's a canonical definition of Laplacian, such a thing is often negative definite, and then you multiply it by -1.
Oh, okay.
Yeah.